Okay, good afternoon, everyone. Today I want to talk about Wslink's virtual machine. So Wslink is a malware loader that we discovered last year. It is likely linked to Lazarus, and all this presentation we will focus on the VM it used to obfuscate these samples, and we will discuss our approach to deobfuscate it. So let's start. I'll skip this introduction slide as I already was introduced, and let's take a look at the agenda. So we'll begin with an introduction into VMs in general and also symbolic execution, because we use it frequently throughout the deobfuscation. After that, we'll cover internals of the VM used in Wslink, and after that explain our approach to deal with the obfuscation, and finally demonstrate it on a piece of bytecode to prove that it works. And I'll also mention that after starting our analysis, we discovered a sample that is not obfuscated, so we weren't motivated to fully deobfuscate the sample, and we'll present it just on a piece of bytecode. So now let's take a look at VMs. So we know that there are two types of VMs, system and process. System VMs are, for example, VMware or VirtualBox that virtualize the entire operating system. Meanwhile, process VMs are, for example, Java virtual machine that allows us to execute application on different operating systems. So how do let me find laser pointer. Okay, so actually virtual machines work sort of like standard machines. For example, they both contain this sort of bytecode, but in standard machines it's like machine code, and it consists of opcodes and operands, where operands are like parameters for instructions, and there are some handlers that basically define the behavior of individual instructions. And when we have bytecode like this, we somehow need to transfer the execution from one virtual instruction to the other, and we use an interpreter for this. And here's an example of how it can work. So we have a function that accepts a VM context, which basically, just like in standard machines, contain some, for example, registers and program counter and things like that. And apart from that, bytecode that is supposed to be executed. So here we fetch an opcode from the bytecode based on the current program counter. After that, increase that and execute one of the handlers. And this can be actually performed in multiple ways. This is actually called direct call threading, because we store all the handlers in this table, and depending on the value of opcode, execute the particular one that is supposed to be executed. And when we execute one of them, we can see that, for example, the instructions can do whatever they want. So the first one fetches two operands from the bytecode based on the program counter, increases that, and then chooses a general purpose register based on that operand and performs an operation. Oops, sorry. Yeah, and this, as I said, it can be implemented in multiple ways. For example, instead of this direct call threading, we can use, for example, a simple switch case, or another technique is called direct threading, where we basically move this call into all the handlers at the end of them. So basically each virtual instructions executes the one that is supposed to be executed after that. And the interpreter only executes the first virtual instruction. So how can we use this for obfuscation? Basically, the strength of this obfuscation technique resides in the fact that the instruction set of the virtual machine is unknown, and reverse engineer needs to understand all the instructions and somehow develop a custom disassembler to remove the protection, and it's really time consuming. So how can we achieve this? So let's say that this entire part, these 4 blocks, are actually located in a separate section inside of a file, that PE file that is supposed to be obfuscated. So we need to have there our custom VM, and then when we take a function, we need to translate it to the instruction set that our VM understands, generate bytecode of that, and then store address of the bytecode somewhere inside of the executable, and replace the original function with a call to our custom VM, and remove the rest of the original instructions. And after that, when the VM is executed, we need to choose the bytecode which is supposed to be executed. We can determine it, for example, based on the caller's address, and then switch our context to virtual, because we were running like in the native one, like we used registers like EAX, EBX, and so on, and we now need to move them to our virtual context. And after that, we can execute the interpreter that understands this context and does some operations on it. And after that, we switch it back to native, so we just move the virtual registers back to native ones, and then continue in the execution. And we can apply this obfuscation, for example, on only specific functions that we need to hide from some reverse engineers. Okay, so let's look at symbolic execution. We'll focus on the implementation in Miasm because we'll use it in our code. And so what it is, it actually expresses code in mathematical formulas, and registers and memory are treated as a sort of symbolic values, and it summarizes code's effects on these symbolic values inside of a basic block. So here we can see it on an example which should make it clear. Basically, when we symbolically execute this ASM basic block, we'll have in the result something like this. So right away we can see what the resulting instruction pointer is, which is like almost the same as this IRDST, which stands for intermediate representation destination, which is sort of a program counter in Miasm. And these two can actually sometimes differ. For example, when we have instructions such as conditional move, we translate it to multiple blocks in IR, and basically we need to add a conditional jump inside of that differs from the EIP. And then we see that there are explicitly defined flags. And apart from that, the semantics are sort of clear, I think. This is the reference of a 32-bit value, and this expression might be a bit more difficult to understand. It's called composition, and it basically says that the first 16 bits of the resulting EAX register are set to the referenced value of ESI, and the other 16 bits are set to the value of EBX. Yeah, and how we can use this. So it allows us to simply apply some known concrete values. So for example, if we know that EDX was set to 96 and the memory value at 96 was set to feed, we can just tell it to the symbolic execution engine, And after that, we can right away see, for example, the destination address. And that's it for introduction. So after the publication of our work, we found out that the VM used is actually code virtualizer used also in Temida, but still the structure hasn't been discussed publicly before, and our deobfuscation technique neither. So still interesting, and when someone finds an unknown VM, he can use a similar approach to get over it. Okay, so let's take a look at the virtualized sample. So we open up the sample in IDA and look at the entry point. We see this function, and basically all the symbols that are in these examples are basically ours. They are not original, they were removed, and we decided to call this function vmm3. So this is a virtualized function, and we can see that the prologue is basically the original one. After that, there's this call to VM entry, and there are just some gibberish instructions. And IDA recognized 7 calls to this VM entry, which means that there are at least 7 virtualized functions. Now, before we jump into what happens in VM entry, we'll say that all over the code, the VM uses junk code, which is basically insertion of instructions that are supposed to obscure the code. So basically, in the right picture, we see a part of the first basic block decompiled by IDA, and we can see that it's really difficult and hard to determine what's going on. Meanwhile, symbolic execution in Miasm, the left one, helped us to simplify this, and we can right away see that everything what's happening in the block is pushing off some registers onto the stack. Now let's get back to the VM entry. So what's going on? So what's going on after that? Basically, there are 7 VM pre-init entry functions, and they are called from VM entry, and they are chosen based on the caller's address, and they are supposed to choose the bytecode address that is supposed to be interpreted, offset of the first virtual instruction that is supposed to be executed, and store CPU flags. After that, all these VM pre-init call one common VM init, which is supposed to save the rest of the native context on stack, and optionally wait for another running virtualized block to end. Because all the threads actually share one common virtual context, so they somehow need to manage and synchronize. And after that, they relocate internal constructs and finally execute the virtual instruction based on the offset. And in this VM, there are actually 45 virtual instructions, and they used direct threading. As I said, every instruction is supposed to execute the following one. And what we discovered is that each of these 45 instructions is again virtualized with another VM that uses the same construct, again some VM pre-inits, one common VM init, and after that there's more than 1,000 another virtual instructions. And the reason is that they are actually duplicated, and we'll get to it more fully after this. And I forgot to mention in VM init that it actually also sets a virtual program counter register and stores a base address that is later used to relocate structures and APIs when they are supposed to be used or called. And it also sets instruction table register to hard-coded value. And all these registers are used by the virtual instructions later. And now we'll look at the first VM2 virtual instructions that are executed in the bytecode. So if we look at the structure of the first one, here we see some RBP in it, which is basically the context pointer. And at the offset A4 is actually the mentioned instruction table. And at this offset 28, it's virtual program counter. So here we actually fetch the address of the next instruction that is supposed to be executed. After that, increase the virtual program counter and set a register to 0. And actually these operations are atomic, so they happen all at the same time. Now the next two instructions, the second one sets several virtual registers to 0, and the third one just stores RSP in a virtual register. And now the fourth one is interesting. For the first time it uses multiple basic blocks, and if we summarize it using symbolic execution, we see an interesting expression. Actually these two virtual registers were set earlier to 0, so we do know what their value should be, and we should be able to simplify it. And when we analyzed multiple instructions that are executed after this one, we found out that actually this construct is used repeatedly, and it is supposed to encrypt operands and parameters of the virtual instructions. And it is actually called rolling decryption, and it's used also in VM Protect, and this technique was described publicly before. Okay, so if I managed to lose some of you, now I'll explain how we deobfuscate this, so you should pay attention now. Okay, so this is the first original block, and we want to apply the known values. We use symbolic execution and just tell the engine that these memory places should be these particular values, in our case 0, and after that we can see that the engine simplified into the following form. Now we see this construct, and again, if we think about this, this is actually pointer to the bytecode, so we access an operand and XOR it against a value. And again, this complicated expression can be simplified because we have access to the bytecode. So we decided to make values that are relative to the virtual program counter or bytecode pointer concrete, and if we apply the engine on it, we can further simplify it. And now it's not only the first block, but we were able to simplify the conditional jump, and now all these 3 or 4 basic blocks do is actually in these 4 lines. So here we actually fetch the value of we get the next instruction that is supposed to be executed. After that, increase the virtual program counter, and at offset 141 is actually the RSP, the stored RSP that I mentioned earlier. And at the end, we actually store a value that is on top of the stack inside of a register, which basically means that this is a pop instruction, because here we increase the stack and here we pop the value, and it is actually atomical, so it happens at the same time. So how can we use this to deobfuscate the entire bytecode? So basically this is a summary of one of the instructions, and we want to build a control flow graph out of this to see what's going on inside of the entire bytecode. And we, during that, treat some values as concrete, particularly rolling decryption registers and memory accesses relative to the bytecode pointer. And we preserve only decryption registers values between blocks to have the actual value that is supposed to be inside of the registers at the time of execution of that particular instruction. So this is a result of the first bytecode. Basically, we can summarize the results into 3 parts, like some intro, outro, and body of the instruction. And actually here we see the virtualized virtual instructions from the first VM. And in the beginning we see that there's a register set to 0, then there's empty block, and actually it contains the initiation of the rolling decryption registers that we just skip because their values are not interesting. After that we store RSP, and then there's a series of pop instructions, and basically we remember that the VM init stored the native registers on the stack, and now we are actually getting them back to the virtual context. Now let's take a look at the outro. And we can see that in the beginning we push the virtual registers onto the stack. After that, pop them back to native ones, and then transfer the control to the next virtual instruction. This is actually sort of a jump to a register, which looks just like the virtual instructions in the second VM. And yeah, these larger empty spaces actually separate individual virtual instructions of VM2. Okay, now let's analyze the bytecode of the first VM. So the first 3 instructions behave just like those in VM2, but the fourth one is again different. It contains lots of basic blocks. This is just a small part of it. And when we inspected the code like more closely, we found out what was the cause. And the reason is instruction merging. Basically, it can perform multiple operations, and the operation that is supposed to be executed is decided based on the operands. So in the fourth instruction, there are, for example, these blocks, and we can see that here's sort of push. Again, we can see the RSP is decreased, actually -8, and a virtual register is stored on the stack. And apart from it, it can also perform pop. Here we see that the stack pointer is increased, and the value at the top of the stack is stored inside of a memory. And we can again simplify this by making these memory addresses and operands concrete, and actually use the same approach as in VM2. We build a graph from the same summaries, treat certain values as concrete, and preserve certain values between blocks, particularly the rolling decryption registers. And we can actually process both VMs at once because we know what memory range belongs to the VMs, as we know the context, and we just treat them as the concrete values, like the entire VM2, and ignore assignments into its context. And now if we look at the results of the obfuscation of the entire virtual instruction, of the entire bytecode of VM1, we expected a series of pops again, but there are some weird conditional branches. And if we look a bit more at the branches, we notice that there's comparison of the virtual context pointer against a hard-coded value, and there were like 2 or 3 patterns like this, and we can just match them and eliminate these conditional jumps because we know what value belongs to RBP in it, and this is actually sort of opaque predicates. And when we applied these values, we actually deobfuscated the bytecode like completely. And the question is, does the approach work? So before we compare our results against the discovered non-obfuscated sample, we will look at some statistics. So In the second VM, the most important thing is the third line. Actually, we were able to simplify around 17,000 executed native instructions to about 300 IR instructions, and it took us like 10 seconds. And in the VM1, we were able to compress more than 3.5 million native instructions into like 400 lines of IR. And since we wanted to analyze only one interesting sample, this is perfectly fine, considering that otherwise we would have to analyze all the 1,000 instructions to know what's going on. And if we use this approach, it simplifies our work and makes it much faster. So let's look at the comparison. So in the left side, there's the virtualized function, and the right side, the non-obfuscated sample. So the prologue is the same, but there's then this difference in this assignment. In the second image, there's the reference, and in the first one, not. But if you look at the results, okay, we see that the reference is applied later on, and actually we can simplify these expressions into a form of pseudocode is not supposed to be ARM to compare it against the original sample easier. And we see that actually there are the two same lines in the beginning, and now if we continue the comparison, we see that it accesses this service status structure, and in the simplified view we see that we load service status structure into a register, and now we use the base address register that I mentioned. We use it to find the current address of the structure. Now we see that in both there's a loop, and if we inspect the body, we see that registers is being decreased, and then we set a memory value based on the decreased register to 0, and it happens in both pictures, yeah. When we continue again, we see the base address register used, and this time we find address of a function and store it inside of a register, and then do simple move. And after that, we call a function, and in the bytecode we do it in a bit more complicated way. Again, use the base address register to find the current address of the API call and store it inside of a special internal register at offset 133. And now if we follow the register, at the end we see that we actually jump into its address, and this basically performs the call. And before that, we set the return address of the call to a function again relative to the base address register, and actually we choose a certain VM preinit based on the operands. And when the call is after the call is executed, we actually jump again to another VM preinit, which means that there are certain blocks of functions virtualized like this. Okay. And to deobfuscate the entire function, we would have to follow the next VM preinit and continue like this. Now, what are the limitations of the approach? Basically, they are the same as symbolic execution, since we use it, and basically we cannot process instructions with unbounded loops using this approach, and we need to address such instructions by other means, for example, some heuristics or manually. But it's not such a problem because most of the instructions do not contain such loops, and for example, move, XOR, and everything you can usually imagine it can be processed like this. And what is the takeaway? We can use symbolic execution to devirtualize some advanced unknown VM in a reasonable time if we treat the right values as concrete. And by advanced, we mean VMs that use junk code, duplicate and merge handlers, and encrypt operands. Okay, so that's it. So you can find the whole white paper at our site, and the source code, which is roughly like 400 lines, is in our Git repository.